Hello everyone. We are continuing learning and we are continuing doing educational videos. And today we will not talk about pure physics. We will talk about how we applied methods that we learned in physics in the finance world. In particular, today we will be talking about portfolio optimization. At CERN Finance Club, where I am one of admins, we have about 150 people who are not just skilled, but who want to put it to next level. We have meetings and then we practice interviews, and some people apply and already quite successfully transfer to top companies. And in our club, we get together and we discuss our portfolio. And our portfolio contains 11 stocks. And let's see, last 7 days we've been doing sort of not bad, 1.5% increase. And the 11 stocks that we have are Sky, Visa, Starbucks, Walmart, Nestle, and so on. But before, we relied purely on sort of expert opinion, on discussions, on some technical analysis. And today we will use a pure science. So pure science will be Monte Carlo simulation. We will simulate with Monte Carlo method um, a series of weights with which these stocks enter our portfolio, and we will find the best set of weights which for a given volatility will increase our return, or for a given return correspondingly will decrease our volatility. With that said, let's put our hands in a heavy lifting. Okay, so let's start with importing libraries. So what we will be using to get prices of stocks, and in particular we will be working with adjusted prices, because over the time um, the price sort of change and we would like it to be normalized. So this is what is called adjusted price. But I'm not going into details about this term. What I will show, you can find lots of resources. What I will show is a pure implementation and the flow. And also I want to mention that what I'm showing today, I learned a lot from Jose Partilla, so kudos to him. Now, I'm importing Quandle, also NumPy. We will be working with arrays, pandas, we'll need for series and for data frames, and of course matplotlib, because we will do some plotting and we'll be looking at distributions, because basically who can stop us from doing exploratory analysis? It's so awesome. All right, first things first, to be able to get information as many times as you would like, not limited to some number of calls, you will have to set up your API at Quandle, where here you will put your key, so you just need to register, and then at your account profile you will see it and you will put it here. Now, how we will get information from Quandle? We can either extract it using Quandle and get method, and if you're interested from some start date and end date, you specify them. Then what I've done, I put it to CSV so I can always reanalyze it later, let's say in a pure Python script instead of using this Jupyter notebook. So this is what I've done. Some stocks I didn't find on Quandle, and or information was for a different time period, but to have it as apples to apples comparison, I use some other sites. So what I've done basically, to a conclusion that I just got all the CSV files for all the stocks that we have. So you can see Bayer and McDonald's and Nestle, basically all of them, and corresponding weights that we have so far, which are optimized by sort of trading group, if you wish. But instead today we will be using algo group, which we are developing, by the way, at CERN. Okay, so what I do first, already prepare CSV files, and I mentioned how you can do it with Quandle. We read it in pandas data frame, and here are data frames corresponding to each of our stocks. Then what I do, I select just adjusted price. That's what we are interested in. And I think PCG ultimately I've got from a different source as well as some other CSV files. So I will have actually to choose specific column converted to pandas series. And because dates are reversed, I will also need to sort it in a non-ascending order. Okay, so I do this for all the stocks. Now, what I will do, I will keep information only for 1000 dates because the available um, data is given for different number of dates. Uh, so I'm just normalizing it to have it equal. And actually, ultimately, PCG, there have been lots of non-values and like really a lot of them, and it's not a tutorial on how to deal with not a number, so I dropped it. Now, what the purpose is to optimize portfolio of 10 stocks. And how we do it? Well, first of all, we create a data frame concatenating all the 10 stocks that we have above, following the column, so x is equal to 1. Names are basically names of our stocks, and there are still a few here and there non-values, so we drop them and we do it in place. Now what I would like to do, I would like to let's run it. Let's run Quandle, import libraries. I will skip this part, don't need it. Read CSV, get time series, normalize the shape, create final stocks data frame. Now what I would like to do, I would like to use head method to look at what we've got, and you see we have values since 2014 September. Now, next, what we can look at is, let's call it mean daily return. And for this, we will have to use so-called percent change method, and since it's daily, so it's 1, I'll have to put here 1, but we want to have it mean, so I will call available mean function. And now I would like to print it. And you can see over a day, on average, Korean stock was negative, bear was negative. These guys had positive return, and I guess maybe BSB was the best one. Sky. So okay, it's good to know. Now let's look at correlations, because it's interesting to see how they are correlated, and when I use a heat map I will show you why. But let's first look at the raw data. So you see there are ones on diagonal, and all the different numbers of diagonal which show correlation, let's say, of Bayer with McDonald's. Why correlations are important? Because well, we can profit from them. So we can profit from them. Let me show you first, for example, correlations for the whole available data. So it will be correlations total, correlations total would be stacks and correlation. And you can see that over a day there is some trend, but we are not interested really in the day, we're interested in total. So here it's way more informative, and you can see negative values because correlation uh, ranges from -1 to 1, and negative correlation means that they are basically changing in a negative fashion. When one increases, the other one decreases. Okay, but enough talking, let's do some visualization. So we import CERN, um, then what we have, we will use this correlation total uh, forward. We will plot it, and we will plot it using a heat map. So let's go ahead and do it. So here is exactly the same information as we had here, but just good to visualize it. And what is interesting to see is this blob, this square over here. You see it's quite, this pink is sort of quite red. It's maybe 0.5, 0.6-ish, and this some may regard as a strong correlation. Now, maybe mention a little bit here why it's important. Well, it's important because, for example, one variable is sort of a few days behind, but we know it's correlated. So once our main variable starting going up, what we can do, we can profit from it because we know that the other variable, which is correlated and few days behind, will go up in a few days. So we have this information, we can use it, and that's why correlations can be interesting. But we will not talk about how to do pair or triple wise optimization of stocks. Today we are talking about portfolio overall optimization, but it's one of possible videos for the next time. Now, what I would like to do, I would like to normalize our stocks. So stocks normalized. Basically, I will take stocks and we will divide it by the first number, and we will use index location 0, and now also let's look at this. So stocks.plot, and let me specify fig option, fig size. Let's do, for example, 16 by 8. So here you can see how since 2014 September till November of this month, of this year, you can see how all the stocks were performing. You can see this greenish, which is McDonald's, was just skyrocketing, right? You can see that this light brown, which is, I forgot what was 3V, but it's not doing that great, in quotes, great. But it's nice to see and note. Now, let's do stock daily return. So we'll do stocks, again, percent change over 1 day, and we will look at first 5 rows. So since it's doing percent change, so there has to be like offset, so first values are obviously nonce, but others are referenced to the first one. And you can see how numbers evolve. Now, what we will use, and I'm not going to discuss it because I want to keep this video short and up to the point, but we will change from sort of abstract value of our returns to normalized, basically log versions. And log versions, just to keep it brief, those are better for calculations, and essentially numbers are not really changed dramatically, but it is useful for the research that we do to be able to do it, and but I'm not going deep into that. So I will just show you how we do it. Log return. Once maybe we will do a video where we will talk about the method specifically, because it may be useful for our other members who are joining our algo group to repeat it and to learn it well. So we will take stocks, we will divide by this stock value shifted by 1, and you will see what it shows. Basically those will be exactly almost exactly the same numbers. You can see 10.3366, 10.313, almost the same, but it is important for our analysis. Now what I want to do, since we used head, instead what I want is to look at the whole distribution that we have, actually all of the distributions. So I will plot it as a histogram, and I will have 50 bins, and figure size, let's have it big. I don't know if it will fit our screen, but let's try. Okay, so you can see for stocks 3V, log returns. For buyer, you see it's kind of nice bell shape. Then for Sky, for Korean stock, McDonald's. Yeah, you see some of them are more picky, some of them are more broad, so they have basically tails are longer, uncertainty is bigger, and we can profit from it just taking into account correlations properly. Now, since we looked at that, what we also can do, we can invoke upon our log returns a method describe. And what it will do for each of the stocks, it will tell you how many we have. And remember, we asked for 1,000 and dropped nonce, so we have a bit less. We have a mean value, standard error, mean and max value, but also percentiles. And it's also useful to know this. Now, what I propose to do is to finally dive into the dessert, the main topic of our video, which is go get the weights using science. So here's how we will do it. We will take a random seed, let's say 1010, for to have an ability to have a reproducible data analysis. So we'll put names of our stocks. We will create random weights using NumPy random generator, and we will create 10 weights because we have 10 stocks. Remember, from 11 we dropped PCG because it had lots of nonce, but also because they didn't have, that particular CSV file didn't have data for 2018 year. Then we'll rebalance it, renormalize it to 1, which is basically take all the weights and divide by the sum. And the reason we do it because they are generated randomly, so there is no way it can know that we need it to sum up to 1, so we have to force it. Now finally we'll do expected return of our portfolio, which is we'll take a mean from our log returns, we'll multiply by weights that we generated, and we'll sum it up. And what is important to note is that we have to multiply it by number of days, and in 365 days in a year, there are 252 trading days, so don't forget to multiply. And finally, our volatility. Um, so actually, maybe let me show you briefly why um, why we calculate volatility like that. So from IPython display import image, and because I want to use some URL file, and from IPython or display import HTML. Now image, finally to be able to print it, let's specify the URL, and URL was located, I have it at the following slide. I always forget how many dashes we need to have. So it's located at iStack at image store under, I had it under U4BGI, I think, but if not, I have here a useful copy paste that we can use. So let's see if it works. Boom, it worked. Now the file is U4B9i that we had. It contained a calculation of variance using weights and this covariance term. So essentially what we will do, we will take a square root of the whole this right hand side, and we will get our standard deviation. So this is what we do. We basically take the covariance and we do dot product with weights, and here is where this mass multiplication, matrix multiplication happens. And then we'll take what we have on the right hand side and we will do a dot product with weights. But don't forget, it's a row vector, it's not a column vector, so it has to be transposed, and that's why we use t. And finally, this will give squared standard deviation, and we need it to the power 1, so we take a square root. And finally, Sharpe ratio. So Sharpe ratio is calculated as return divided by volatility, which is return over standard deviation or error. And in physics, it's something like math significance, which is normalized to the error, or significance of impact parameter if you work with jets. And it can be, for example, SIP 3D, which is significant of impact parameter in 3D space. And this method is used in finance, and it's called Sharpe ratio. So with that, let's get the info. So those are our stocks. Those are the weights that we randomly generated. We rebalance them to have a property that they all sum up to 1. And with the weights that we generated, we get the following 1% return. Expected volatility is about 17%, and Sharpe ratio is kind of low. It's 0.05, but that's what we have. It's okay. Now what I suggest is to use more simulations, and here I prepared a quick cell to run, and it will run about 1 minute. So when runs, let me tell you what is happening. So it's working, and we've got about 1 minute. So I import time library to be able to see how long it will run, and we will have 50k simulations, 50k simulations of those random weights, because we will sort of try, if you wish, random grid search, and would like to see what are the weights with which our sharp ratio would be the best, because the higher sharp ratio is, the better, because it means for a given volatility, your return is as high as possible. So we create, first of all, for all weights, NumPy array, initialize it with zeros, and length is 50k. Now we create return array, we create volatility array, and finally our figure of merit sharp ratio array. And for I, for index in the range of our simulations, which is do at 50k, what we will do, we randomly generate weights, we normalize them, we store in our all weights variable, we get expected returns, which is, again, remember, log return, mean value times the weights that which are generated, sum it up, and don't forget that we do it in a year only 252 days. Then to get volatility, as we discussed, first multiply covariance matrix by weights, then multiply transpose weights by the result of mass operation here, take square root. Finally, for each index, because we will simulate 50,000 different sharp ratios stored in particular under particular index in a sharp array. So, and you see we are done. 70 seconds passed, and we have our array of sharp ratios, and we will look at it in a second. But what also I would like to do before we go to the cell, I would like to look at sharp array max value, like what is the highest sharp ratios that we had in those 50k simulations. And you see it's 0.75, so way better than just one single random guess. Now, where it is located in our array, and for this we will use argument under max, argmax, and you see it was 12k 572nd simulation that led to this nice sharp ratio. Now, what else? Well, if we know where it is located, we can look at array of our weights, of all the weights that we stored. Remember, we had all weights array, and see what is the set of weights that leads to this perfect sharp ratio. So all weights. Now, how we do it? We take our sharp, add the argmax, and after executing the cell, we see those are the weights with which 10 stocks that we had entered over here, Korean, Bayer, McDonald's. Those are ideal for under our simulation weights with which stocks should enter our portfolio. Okay, now let's plot all those simulations. Let's plot our best sharp ratios that we found, and let's plot the point where we are right now without using this, let's call it advanced, but sort of math, right? Our Monte Carlo method. So percentage, how much cash we put in our stocks is over here, but we dropped PCG, so here's what we have. Now for total, I sum all of them, I normalize it, and I have the following weights which we have for our portfolio as it is now before we implemented our optimization, that I will be presenting actually in 3 days at our next meeting. So now what we will do, we will print what we have currently, we will print expected return current multiplied by 252, and we will plot also expected volatility. Don't forget also how we do it. We've done it already a few times. And what we see is that return can be 0.03 and expected volatility is 0.18. Okay, good to know. Now, again, don't forget, this is what we have now. However, since we've done the simulation, what we can do, we can plot it using matplotlib. So we'll do a scatter plot, we'll plot return versus volatility, and we will use a color map winter, and we will look at Sharpe ratios at 50k Sharpe ratios that we generated. We will plot here maximum signal maximum Sharpe ratio return and maximum Sharpe ratio volatility using those argmax functions that we utilized before to locate the best Sharpe ratio in the whole simulation. And also here we will plot the ones that we have right now, which we plotted here, and which I showed you how to normalize over here. So that's plotted. Okay, so this is return versus volatility, and here is a color map for Sharpe ratio. You don't want to be at the bottom because where the blue is, because Sharpe ratio is low. You want to be at the top. The greenish, the more green it is, the better, obviously, right? So you would like to be somewhere over here, and at the second video we will talk about efficient frontier curve, and where that curve touches the tangent, this is where you would like your portfolio to be. But we will talk about it at the second video. For this particular video where we use Monte Carlo method, those are the points that we generated. You see these are sort of bluish, they're not so great. These are greenish, a bit better. And here is where we are, and here is where ideally we should be based on our simulation. And that's it. As you can see, there is quite a room of improvement. We can basically go from 0. I don't know, 85-ish to 0.3, right? We can decrease the volatility, which is good, keeping the same return. But once we reach this point, we can increase return, going up to the best Sharpe ratio point, and we can sort of fourfold it, right? Going from 0.25 to 0.1, paying nothing for this because, hey, it's available. Just use better weights. So here is how we've done it. A quick summary again. We started with importing all the CSV files that we either prepared separately or downloaded from Quandle. We've got adjusted close prices. Then we extracted only 1,000 days. We created our total data frame for all our stocks. We looked at percent change over 1 day, mean value for each stock and for all the correlations. Then we plot for the whole portfolio correlations among all the stocks. We notice there is some interesting stuff going on over here, which we will hopefully explore soon in the next one of next videos. We looked how all the stocks performed over the course of about 3 years. And we also looked at each distribution of returns individually, in more specifically of log returns. It's an important thing before we start doing our analysis. Then we used the formula over here, which gives us the volatility, and we implemented it at this line. And we, with the code in this cell, we looked at what a random weights set can give us in terms of volatility and Sharpe ratio. Then we run 50k simulations of random weights. We've got return volatility and ultimately Sharpe ratio for each simulation. And what we've done, we also looked at where we are right now, which is without Monte Carlo simulation. And finally, we plotted a scatter plot of all simulations with the best Sharpe ratio dot on top, as well as a present state. And one sees clearly there is lots of room for improvement. And in the next video, we will look at another method, how we can deduce sort of the same results using a minimization technique, which is we will try to maximize Sharpe ratio, or more specifically inverse of that, doing a minimization. And there are several libraries available in Python for minimization, and you will use SciPy. But the conclusion is still the same. We can decrease the volatility and increase in return at the same time, and isn't it great? That's it. Methods similar to this, a bit more involved, we will discuss at the CERN Finance Club. I'm not keeping it here because this is developed internally within our group, and this video is going to be public. So for public, this should be enough. Thank you for watching. Stay hungry, stay humble. Till next time.